read it hard again. We're going to get through this part, which is pretty short, and then we're going to begin the next part. One of the things, among others, that I want you to get a handle of from this class, if you don't already know, how come as we orbit the sun, how come the Earth goes through seasons? Okay, so we'll be talking about that just kind of briefly. This actually is the Earth broken up into coordinates. Okay, what do we call these guys? Like going across horizontally. That's letter L. They both start with letter L's. These are actually what I was after. These are called latitudes, like lines of latitudes. Yeah, from the equator. We have south equator latitude, north equator latitude. Very good. What are these? I'm going to find the prime meridian. What are these? Seriously, gosh. I am so challenged when it comes to, there it is. It's over here. Here's 0. Okay, so what are these if we go east or west of the prime meridian? Those are called longitudes. Yeah, very good. This isn't on the slide, but what do we call this? Starts with the letter C. Celestial sphere. This is called the celestial sphere. Yeah. What are those dots? Stars, yep. And actually the celestial sphere is also, and it's not on here, but they're definitely maps that breaks the celestial sphere down into coordinates, just like the Earth is broken down into coordinates. Now, are all the stars the same distance from the Earth? Yeah. Okay, very good. This, we talked about the international date line. Anybody here ever been to the international date line?
So Sweet Life is Cody.
Sweet Life is Cody?
Sweet Life on that.
So the deal about the international date line is if we find a prime meridian, which is 0 longitude, if you go just opposite, okay, just opposite, that's where this should be east or west. That's where the west and the east meet up at the international date line. Okay, so you're on this side, you're on one day, on this side, you're on another day. Very confusing. This is where the international date line is. Wait. Would that be right? Yeah. It says it's arbitrarily drawn. It's basically where, like I said, the west and the east meet up. All right, so here we go back to, of course, we see the sun. What's the blue? What's the blue circle? The eclipse, the plane of the ecliptic, yes? And the blue circle is how the Earth is orbiting the sun. What direction is the Earth orbiting the sun? Counterclockwise, looking down at the North Pole. Perfect. So what's up with the Earth's axis of rotation? It's tilted, exactly. Exactly. And so it's tilted like this. And I already kind of talked about this. We'll talk about it a little bit more. But if this is the Earth's axis of rotation. Okay, and this is the sun. By the way, that video we watched the other day, I love the questions you came up with. I haven't given them back to you, but I will. Good job on your questions. That it talked a little bit about kind of the way the moon was formed, and I think it talked about maybe the Earth's tilted axis of rotation. They honestly think that the same thing that formed the moon, that same impactor about the size of a small planet, actually gave the tilt in our Earth's axis of rotation. So, yep, here we go. This actually, now sometimes people think, well, yeah, this would be summertime in the northern hemisphere. You guys know that the northern hemisphere and the southern hemisphere have opposite seasons. That's one thing why Christmas just drives me nuts, because at Christmas time, so this is summertime, we're going counterclockwise, okay? So this will be fall, this is kind of where we are now. This would be winter time in the northern hemisphere. It kind of drives me nuts. What do people tell their kids about, I don't mean to burst anybody's bubble, but about Santa Claus? What do they tell their kids about Santa Claus? Because Santa Claus can't have a sleigh because it's like all hot down there in Australia, the southern hemisphere. But anyway, so it keeps the same tilt. I have a video to show you. I like this video. See if you guys like it. See if it will play. So I like the video because they talked about the whole angle thing. So to me, and there's actually, I think, one more element. But did you see where the sun's angle changed? In the wintertime, does the sun get very high for us? Even during the day, it appears to rise kind of in the east, well, east-ish, and set in the west, but it's kind of southeast and southwest. It never gets very high. But in the summertime, the sun does get high. And when the sun has a greater angle, though this would be the light beam from the sun that has a greater angle, and it goes through less of the Earth's atmosphere, and that shaft of light from the sun has to only spread only a certain amount. That's why the sun in the summertime is so intense. Sun in the summertime is more intense than the sun in the wintertime. So here's in the wintertime at noon, that might be how high the sun gets. So two things, that shaft of light coming from the sun, it has to actually pass through more of the Earth's atmosphere. But what this is showing you is, can you see the area that shaft of light from the sun goes over, that same ball of light? Instead of 1.04 area, 1.04 meters squared, it goes 2.24 meters squared, so it's spread out. So even at noontime, the intensity of the sunlight is not as great, which can be good or bad in the wintertime. So a few things here. Again, somehow I will ask you some questions on your test about this. So this is the whole. So you need to pay attention because there might be something on the test on this. So this is the whole. The 4 points of the year as we orbit the sun. Okay, now hopefully you picked up the whole, the northern and southern hemisphere seasons are switched around. Okay, in the wintertime, if you're at the Arctic Circle and you're a vampire, you're very happy because there's no daylight. Even as the Earth spins on its axis of rotation, you don't see the sun. So we have 2 solstices and 2 equinoxes. Winter solstice, summer solstice, the vernal equinox, sometimes called the spring equinox. And the autumnal equinox. So you're going to want to know those dates. This actually down here is showing you, if you go, say Alaska, I don't know if that would work. In the sun will never set. Like around the summer solstice, the sun is up all night long. And so that's kind of what's showing you the path of the sun. It gets low, but it never sets. Has anybody ever been to Alaska and seen that phenomenon? No. All right. So this is just kind of reinforce what we saw. Sometimes on the test, I will ask you these key lines of latitude. So what's this line of latitude right here?
Equator.
It's the equator, 0, equator, perfect. And just like the video said, there are actually 2 lines north and 2 lines south that are really important. So here we go. Equator, 0 degrees. Oops. Tropic of Cancer is about 23.5 degrees. 23.5 degrees. And actually, on the video, they talked about how that in at the summer solstice, that's actually where the sun's rays are most intense. Also in the northern hemisphere, or in the southern hemisphere, we also have a 23.5 degrees. It's the Tropic of Capricorn. And then we have 2 circles, Arctic Circle and Antarctic Circle. And these are about 66 degrees or so. Okay, so this is actually showing you, let's see, rays are most intense. I can't tell. This is the summer solstice, they said. So rays are most intense at the Tropic of Cancer. This is the winter solstice. Rays are most intense over the Tropic of Capricorn. Just like the video said. All right, so what's this? Celestial sphere. I just love that. And we talked about celestial sphere before. To get the celestial equator, which would be kind of, if you can see the Earth in there, the Earth's equator is kind of right here. If you just extend out, then you get the celestial equator. So that's the celestial equator. Extend it out, you can kind of see it's the dotted line here. This is the celestial equator. But the ecliptic is where we're going to actually see the planets, and it's actually tilted 23.5 degrees. All right. So one of the things, I'm glad that you guys have that sheet I just gave you. Do you have to answer all of these questions? No. How many do you need to answer? 3. Perfect. Okay? So we're all on the same page here. All right. So let's take a look at the next part. Looking at kind of just briefly the history of astronomy. And there's so many examples of ancient people who actually were so bright with regard to their observations and predicting what's going to happen in the sky. I like to think of kind of, going back 100 years, 200 years, 300 years. The sky was like entertainment. They would tell stories about what they would see in the nighttime sky. But it was also practical because if you were an agricultural society, you can use what's happening in the sky, the seasons, to understand when to plant and all that. So this actually is to kind of tell you, if you read about the science of astronomy, where did it start and all that. Well, I don't know about necessarily where it started, but there was a city in Alexandria in the Middle East that was great for, at the time, back in the, I don't know how long ago, but about collecting information, collecting knowledge. Unfortunately, during one of the wars, it was raided and destroyed. But this is kind of talking about including the knowledge of astronomy. I mentioned when to plant. And we're going to talk about phases of the moon, but this is a phase of the moon. The phase of the moon is actually it's in right now. It starts with the letter C. C-R. It is crescent. It looks like it's something you eat. This is a crescent moon. And what they used to look at was to kind of see how the crescent moon was tilted to know that those bars right there are precipitation, to know when to plant. Okay. What's this? You recognize it? It starts with letter S. Famous place?
Stonehenge.
Stonehenge, yep. And it's like they also understood how to place those rocks so that, how does this work? I think it's solstices, if not both the solstices and the equinoxes. They place those stones so that they line up just perfectly with the sun at these important places as the earth goes around the sun. So the sunlight, it will make these shadows. So that's pretty cool. 2750 BC. Here's one for you, a little more modern. What does this look like it might be?
Sundial.
A sundial. It's a big honking sundial. Yep. Yep. And I've got one in my office, but as the sun, whether the sun is low because it's winter or the sun is high because it's summer, if you have a sundial, it will cast it. You can put it right and it will cast a shadow what time of day it is. So, that's pretty cool. This, and it's amazing that we can find these. This was a Native American, I believe. And the deal here is, can you kind of see the etchings there? And what they did was they had the etchings on the rock here, and they had the slit on the rock here, and it lines up again right on the solstice. Summer solstice at noon, that dagger, that dagger of light from the sun goes through the bullseye. Really? So cool. I mean, you know. This is actually then leaving the Americas. This is thank you, South America. Another culture of Indians, natives, I should just say, that built their city around what was happening in the sky. There's one. Okay, it looks kind of modern, doesn't it? They wouldn't necessarily have a compass, but what they would do is have this lattice thing, and they can hold it up to this pattern of stars in the sky to know what direction they're going. So you line those little dots up in the sky. It's a navigation tool.
Okay, but like,
During the daytime?
no, stars aren't always in the same place, are they?
Stars aren't always in the same place. Stars will, over the course of hundreds of thousands of years, kind of make different patterns. So
it's still accurate.
So it's still accurate. Maybe what you're thinking of is we looked on a slide where if a star is close enough, it will change against the background stars. So you are not losing it. You're right. We said stars are not always in the same place. And some stars, we call that parallax. Some stars, if they're close enough, when the Earth is here, 6 months later it's here, it will look different against the background star. I have a video to kind of show you this. Can't pronounce his name, Aristophanes. I'm going to kind of talk you through some important people in the science area, and then actually Stephen Hawking was, hey ma'am, I can't think of it. Who was also, Stephen Hawking has made a lot of great advances in astronomy. Stephen Hawking's ideas actually kind of match up with Einstein's. He's kind of on the same path. He was, excuse me, Stephen Hawking has passed away. Yes, he was. What's that? R.I.P. Stephen Hawking. Yep. Awesome. So here's the deal for you. You know, we've been talking about the sun's there and the Earth goes around the sun and the other planets orbit the sun. That's how our solar system's set up. But that wasn't what we always thought was the case. This with the sun-centered is called the sun-centered model. Another word for sun is helio, so heliocentric model is how we know the Earth to be. And actually, yeah. But that wasn't always the case. What do you think the geocentric model is? You can kind of read on the slide. What's the geocentric model? Instead of sun in the center, what's in the center? Geo meaning Earth. Geocentric model. And this actually, I don't know if this looks like the Earth to you, but there's the Earth in the center. And then all of the stars orbit the Earth. The planets orbit the Earth. The sun orbits the Earth. The moon really does orbit the Earth. Okay, the geocentric model of looking at our solar system. And actually, we smile, but that was more predominantly what was thought before Copernicus came in and made a big thing about it. So, kind of yin and yang, the opposite of the geocentric would be the heliocentric model. Okay, so I mentioned Copernicus. But actually, before Copernicus, clear back in 260 BC, Aristarchus had it right. Aristarchus had this idea that we all know to be the truth, that the planets orbit the sun. Looks like if you're following along, I kind of moved my slides around a little bit. The way you pronounce this scientist's name is Ptolemy. The P is silent. Okay? So Ptolemy was kind of the last gasp for the Earth-centered model. Here's Ptolemy's idea. He puts the Earth in the middle, the stars and everything orbit the Earth, which is no problem necessarily. The sun orbits the Earth. What kind of gets difficult, and we'll talk about this momentarily. So guys, so no cell phones, no going to sleep. Okay, if you need cell phones, if you need to sleep, then I think it's distracting everyone. So one of the things that they had to explain was this idea of the planets. So the planets actually tend to kind of wander backwards, and we call this retrograde motion. So it has direct motion and has retrograde motion. And so what Ptolemy did was to go ahead and put those little planets orbiting the Earth. So this is having the Earth at the center of everything, which we know is not true. But he said the planets orbit the Earth, but they kind of go through these what we call like little loop-de-loo or little epicycles. So this would be what we call direct motion, okay, as a planet's orbiting the Earth, okay. But then as it kind of goes back here around this little epicycle, that is the backwards or retrograde motion, okay. So that's how he made sense of the planets. So one of the things about planets is planets will be against different background stars. I haven't made much to do about it, but if you pull up Stellarium, you'll see that we've definitely got planets out this time of year, or right now anyway. We've got Venus, that's the sun sets kind of in the west. Then we have Jupiter, Saturn, Mars. They're all kind of up there, which is unusual. Kind of a feast of planets. But those planets will move against the background stars, and I kind of get my east and west mixed up, but they will move eastward, and that's what we call direct motion. They will stop then and appear to go backwards. So the direct motion made sense. If the planets are orbiting the Earth, what did not make sense was this reverse direction, this retrograde motion. So I have a video to kind of show you that retrograde motion, like what's being shown here. So the inner orbit is Earth, and this could be Mars orbit, and you told me that Earth is moving faster. So you see segment A, B, C, D, and E for the Earth, versus A, B, C, D, and E for the yellow planet Mars. Just like he marked out in the sand, usually we have this direct motion. And the direct motion would be the A, the A and the B. That's direct motion. Okay? Then when we get to the C, you can see what's happening with this region is that the Earth is going faster, like you told me, and it's overtaking Mars. So you start to see kind of Mars go backwards, which is retrograde. I'll put R here for retrograde, D for direct here. And then D here, when Earth gets sufficiently far away, then we go back to direct motion. So this is D.
Will it do that all the way around then, or does it only do it one time?
So the direct motion would be all the way around, and retrograde just is when it's overtaking the planets. And it's, I don't know, if you drive much on like a freeway sort of thing, honestly, this is kind of a similar sensation I feel anyway when I'm kind of overtaking a car. If you look to the background trees, it kind of feels like, whoa, everything's kind of moving backwards just at the time when you're kind of going past that vehicle that you're both moving. So it's kind of a similar sensation. But that's for me anyway. Here's another figure, a couple figures to show you the same thing. It's all about, it's all about sun-centered. And here we have, this would be the Earth, and this would be Mars. Of course, we have the Earth here and Mars here to kind of show you. It's as the Earth goes faster than Mars that we start to see this. So if you look at positions 4 and 5 especially, what's happening is we're overtaking it. It being the planet Mars. So Ptolemy, let's just see if we're on the same page. Ptolemy, do you guys remember which model was he? Did Ptolemy put the Earth at the center, or did he put the Sun at the center? He put the Earth at the center, Ptolemy. One of the tenets of good solid science is that it's not complicated, and we say that Ptolemy, when he introduced his cute little epicycles, that made it complicated. So keep it simple, stupid, he did not. Copernicus was actually, I think, of kind of a turning point beyond Ptolemy. So Copernicus went out there and like, no, things are really looking like it's not the Earth at the center, but it's the Sun at the center. So let's see how he did that. So here we have Sol. My mom was like this morning, she's so cute. We talk about science and stuff on the way to work. She's like, so there are other stars out there, there are other solar systems. And I'm like, well, because we've talked in here, most stars have planets, but we don't call them a solar system because the word soul is our star. The word soul is our sun. So we call them, those other stars with planets, we just call them another star system. Okay, or extra solar planets. But anyway, so yeah. Let's take a look at, so Copernicus was a turning point. There are a few names I want you to know. I mentioned Ptolemy, okay, Copernicus, turning point, Tycho Brahe. Let's see what this video does. Tycho Brahe, I like to think of him as kind of okay, well, let's pick up here let's take a running start at this on Friday. Everybody looks ready to go out to the picnic.
I got another class.
Drat.
No, I don't.
Well, if you don't have class, you should go out and get something to eat and check out everything.
I'm going out there during my public speaking class. It'll be about 12 o'clock.
I had that last semester.